All right, so we're moving on with Giancoli, and Giancoli chapter 9 is going to talk about equilibrium. So, equilibrium is just exactly what it sounds like it is, where all the forces are equal. So, object of force acting on it but not moving is said to be in equilibrium, right? All equal. So, like textbook on the table, the old standard gravity goes down, normal force goes up. They're equal but opposite. You're in equilibrium because you're not moving. So the first condition for equilibrium is that the forces along each coordinate axis add to zero. So all your x's are zero, all your y's are zero. If they're along the axis, obviously they are what they are. But remember, if they're at an angle, then we have to do x and y off of that. Okay, and that'll be useful to know that each coordinate axis will add to zero, and that will help you look at situations and kind of gather information. Okay, so that's the first condition. The second condition is that there is no torque around any axis, but the choice of axis is arbitrary. Okay, so no torque, and you can choose where the axis is at. So like in the previous example here, you can see that we chose this as our coordinate, as our origin, and then our axis goes like this, and that just helps us get more on the x and y, and we don't have to do as much trig. I mean, we could have made this our y and x going down here, then we would have had to do a little more trig. So we can choose the axis, is what that means. So let's do some examples. Straightening teeth, the wire band shown in figure 9.3a has a tension force of 2 newtons along it. It therefore exerts forces of 2 newtons on the highlighted tooth to which it is attached in the two directions shown. Calculate the resultant force on the tooth due to the wire, Fr, force resistance, okay? And we'll draw it up and look at it on the board. Do it now.
All right, so here's our little drawing, I guess. We want to find the resulting force if the tension force, all right, going amongst these teeth on the wire bend is 2 newtons. Now, you go to the orthodontist, they fix these braces. They want to try to make them equal on both sides if we want the force to be equal. Obviously, if your teeth need to be bent differently, they can tighten one side and make one side a little bit looser so they can get a different resultant force, maybe even change the angle. But here they're equal, right? So they're at 2 newtons. And we want to find the resultant force. Now, because they're both here, it's going to be additive. So we're going to find the resultant force here, and then add them together. So this is 70 degrees here, so obviously we have a right triangle that's formed, and we can find this resultant force by using cosine. So if we take 2 newtons times the cosine of 70, 2 newtons times the cosine of 70, we can find Ft in both directions. So 2 times cosine 70, 0.68. This also is 0.68. Now I know they're going in different directions, but they're going to come together for this resultant, right? Because they're both in the same line. So even though these forces are going opposite directions, they're going to come together here. So this is going to be 0.68 plus 0.68. So 0.68 times 2, 0.68 times 2 gives me 1.36 newtons. And that's going to be my resultant force here. Again, just adding them both together, we're in equilibrium.
Chandelier chord tension. This is the one that was on the that you saw earlier. Calculate the tensions Fa and Fb in the 2 chords that are connected to the vertical cord supporting the 200 kilogram chandelier. Ignore the mass of the chords. And this will be an interesting one for us to look at. Do it now.
So here we got a chandelier. It's in equilibrium. Our x's and y's are all going to be equal. So this is totally, the FB is totally on the x. This string's, it's totally on the x. This string's totally on the y. The FA is what we're trying to find here. Okay, so FA is going to be going in 2 different directions here, all right? So at the 60-degree angle, FA on the Y is going to be FA, and this is opposite, right? So katoa, opposite sign. So this is sine of 60. And then the x component, FA of x, is going to be FA cosine of 60, because that is adjacent. So I have my x's and y's. I know that this is going to be equal to FB, so FA cosine of 60 is going to be equal to FB, because we're talking about the x, and on the y, FA sine of 60 is going to be equal to this, which is going to support the total weight of this. So it's going to be 200 times 9.8, mass times g. To find FA, I divide by sine of 60. So 200 times 9.8 divided by sine of 60 gives me FA to be 2263 newtons. So I found FA at 2263. Now to find FB, I just go to my other equation. I substitute this in. 2263 times the cosine of 60 is going to be equal to FB. So 2263 times cosine 60, FB is equal to 1132 newtons. So by keeping things equal, we can kind of work some magic here with the numbers and find these two forces pretty easy. And so if we think about it, and I'm just going to give you this, I get 200 times 9.8, I got 1960 weight pulling straight down, but then I've kind of leveled it off by putting it into the wall here, that I can take some force that way, and then FA can go some force that way, and I can make this thing work.
And then levers. So the bar that you see here, right, that the guy's holding, is being used as a lever to pry up a large rock. So we're trying to lift this rock. The small rock is the fulcrum, the pivot point. The force that's going to be pushed down on, so FP, required at the long end of the bar, can be quite a bit smaller than the rock's weight, mg, since it is the torques that balance in the rotation about the fulcrum. If, however, the leverage isn't sufficient and the large rock isn't budged, what are two ways to increase the lever arm? And we'll talk about that one by looking at the board. Do it now.
All right, so here's our situation. We got the mass, the weight of the boulder times the distance from the one end of the pry bar, I guess, lever to the fulcrum, and then we have the other distance from the fulcrum to the person applying, and then that's the force applied. So here's what we know. I know that for this to work, mg times that distance, r, is going to equal r times fp. Okay, and then if I want to find ways to, what are we trying to do? We want to, the large rock isn't budged. What are two ways to increase the lever arm, right? We want to increase the length of r, because if the more r we increase, the less force we need to apply, all right? So the more r we increase, so if we can make this longer. So the first thing we could do, and I know it seems like magic, right? But I make this longer. If you have a tool, pry bar, and you're trying to pry something that's not working, take a pipe, and it can, I'd use a metal pipe, but PVC would work. And if you put the pipe on, it lengthens your arm. If you can lengthen this arm, this will be less force required to move the boulder. So something to lengthen the arm, either put a pipe over it or something to that extent. Now, the other is, if I want to make r bigger and I don't have that pipe, what do? Well, I take my fulcrum and I can just move it in. Now, when I do that, right, when I do that, once again, this r gets smaller this R gets bigger, which makes this number get smaller. So in the end, we'll be able to get that to work also. So moving the fulcrum in closer, which isn't huge, but if you can make the lever arm longer, obviously that would work the best.